In this video, I want to talk about Markov chains. In many dynamical systems, the states of the variables are not known with certainty, but can be expressed as probability. These dynamical systems are called stochastic processes. And for a stochastic process, we need a couple of things with our probability. All of the values need to be between 0 and 1. They can be 0 and can be 1, but they should be between and including 0 and 1. And if I add up all of my probabilities, I should get 1. So the sum of all of the probabilities should be equal to 1. Whenever we talk about our matrix, x of t, that contains x1 of t, x2 of t, all the way down to xn of t, depending on how large my system is, I would need each one of these values to be between 0 and 1, and I would need them to add up to be equal to 1. If I add up the entire column, it should be equal to 1. And this is known as a probability vector. We can also have what's known as a stochastic matrix. This is a square matrix, each of whose columns is a probability vector. So in my previous video, I did an example where x1 was equal to 0.45, and we can see that this is a probability vector. The values are between 0 and 1, and they add up to 1. In this example, my matrix was 0.8, 0.1, 0.2, 0.9. And this would be a stochastic matrix. 0.8 plus 0.2 is 1, 0.1 plus 0.9 is 1, and all my values are between 0 and 1. So this is a stochastic matrix. And these matrices commonly occur in formulas that relate successive states as a stochastic process. So, for example, in this case, they were related by k plus 1 is equal to p times kx, where this matrix is my matrix P. In this example is a special case of a large class of stochastic processes called Markov chains. A Markov chain is a dynamical system whose state vectors at a succession of equally spaced times are probability vectors, and for which the state vectors at successive times are related by an equation of this form down here, where P is a stochastic matrix. So we need xk plus 1 to be equal to p xk, where P is a stochastic matrix. And the entries of this matrix, Pij, is the probability that the system will be in state I at time k plus 1 if it is in state j at time t equal to k. And this matrix P is called the transition matrix. So let's do an example of getting this transition matrix. Let's suppose that a tagged lion can migrate over 3 adjacent game reserves in search of food: Reserve 1, Reserve 2, and Reserve 3. Based on data about food resources, researchers conclude that the monthly migration pattern of the lion can be modeled by a Markov chain with this transition matrix. So what this means is each column is going to represent what happens at time k. Each row is going to represent what happens at k plus 1. So we're going to set up a picture to kind of demonstrate what's happening here. Here I have 3 boxes that represent Reserve 1, 2, and 3. So I'm going to start with the first entry, this 0.5, in the first row, first column. That tells me that there is a probability of 0.5 that if they're in Reserve 1, if the line is in Reserve 1, it stays in Reserve 1. The second entry in the first row is 0.2. That tells me the probability that it moves from Reserve 1 to Reserve 2. So this probability would be 0.2. The third entry in the first column is 0.3. That's the chance it'll move from 1 to 3. So the column tells me where I'm moving from. The row tells me where I'm moving to. If we move to the second column, we're now looking at where they go from Reserve 2. 0.4 is going to go to Reserve 1. 0.2 is going to stay at 2, and 0.4 is going to go from 2 to 3. The third column is going to represent reserve 3. 0.6 is going to go to reserve 1. 0.3 is going to go to reserve 2. And 0.1 will stay in reserve 3. Let's suppose that we release this lion into the wild in reserve 2. So my initial vector, there is a 0 chance he's in reserve 1, a 1% chance he's in reserve 2, 0% chance he's in reserve 3. So he's definitely in reserve 2 since we are dropping him off. Well, then we can start tracking his location based on this. So I have my matrix P, which I will rewrite. 0.5, 0.4, 0.6, 0.2, 0.2, 0.3, 0.3, 0.4, 0.1. And if I multiply by my initial vector, my 0, 1, 0, I get the vector 0.4, 0.2, 0.4. So this is x1. So after one time unit, we know that or 1 month, we know that there is a 40% chance he's in reserve 1, 20% chance he's in reserve 2, 40% chance he's in reserve 3. If we continue this, use our same matrix, and multiply by x1, 0.4, 0.2, 0.4, we get 0.520, 0.240, and 0.240. So after 2 months, there's a 52% chance he's in reserve 1 and a 24% chance he's in reserve 2, a 24% chance he's in reserve 3. And we can continue this process and continue multiplying things out. If we do, we get that x3 is equal to 0.5, 0.224, 0.276. x4 is 0.505, 0.228, and 0.267 approximately. 5 months later, we're at 0.504, 0.227, and 0.269 approximately. And then x6 is approximately 0.504, 0.227, and 0.269. So we can see that the vector states here, the state vectors, seem to stabilize over time with a probability of approximately 0.504 that the lion is in reserve 1, approximately 0.227 the lion is in reserve 2, and a probability of approximately 269 that the lion is in reserve 3.